Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. So, you may recall that in the last two lectures, we had considered two types of analysis of variance: two-way analysis of variance with and without interaction effect. Now, have you thought about that you simply assumed that the interaction effect is entering into your model in an additive way? Well, that was also not your choice, because you had parameterized your model, or in fact you had reparameterized your model in such a way such that the interaction effect was entering into your model in an additive way. But now, once you are trying to do a real data analysis, you have absolutely no idea that when you are trying to consider the interaction term in the model, whether that is entering in an additive way or something else. And based on that, your statistical conclusion may also change. Means as long as your interaction or the interaction term in the two-way model is entering into an additive way, your statistical inferences, whatever you have drawn up to now, they will remain valid. But in case if this assumption is violated, then something else will happen. So, this is very important for us to first try to find out whether this interaction term is entering into my model in an additive way or not. Means, can we write something like alpha I plus beta j plus the interaction effect or not? And the second question is, how are you going to handle this interaction term? The effect of factor A or factor B, that you can control, but how are you going to control the effect of interaction effect between the factors A and factor B? And the more precisely, if I try to say, how are you going to express the interaction effect between A and B? So, one of the simple approach that we follow in statistics is that we try to write down the interaction effect between A and B as the effect of A into effect of B. So, now if you are trying to assume this format, well, we are actually going to assume this format in the further lectures, particularly when we are trying to do the factorial experiments. So, it is important for us to know at this moment that when we are trying to assume this particular type of structure for the interaction effect, then this interaction effect is entering into my model in an additive way or not. If yes, only then whatever analysis we have done here or whatever we are going to do, that will remain valid. So, now in this lecture we are going to develop and learn one such test which will help to find out whether the interaction effect is entering into the model in an additive way or not, where the form of the interaction effect is given by the product of their individual effect, and this test is called as Tukey's test of non-additivity. Well, when I am doing this test, I would like to have your attention. I will go very slow. Why? Because at some place while doing the algebra, there can be some confusion, and that confusion will be something like whatever is the standard language or terminology of statistics, that will not indicate the same thing what we use to expect from it. What does this mean? This I will explain you, but my intention at this moment is this: I just want to request you that you please try to follow these steps very carefully. I will try my best to explain it in a very simple way, but you also try to understand in the way in which I am requesting you. Right. So, let us begin the lecture and try to understand this test. Okay. So, now if you see, we are going to consider the setup of two-way classification with one observation or cell and interaction effect. So, that we already have developed when we did the two-way analysis of variance and with the one observation or cell. So, we have developed this model y I j is equal to mu plus alpha I plus beta j plus gamma I j plus epsilon I j, where I goes from 1 to capital I and j goes from 1 to capital J, with the constraints that summation alpha I is equal to 0 and summation beta j is equal to 0. Now, first I try to show you that under this case how are we going to face a trouble when we try to consider the distribution of degrees of freedom, right. So, now if you try to see here, you had obtained that you have here two sources A and B, and the third source is their interaction, say A B, and you had found earlier that the degrees of freedoms which are associated with A, they are I minus 1, with B they are j minus 1, and the totals are here I j minus 1. So, now if you try to see here, you have here two more terms A b and error. So, in case if you try to find out, or if you try to recall your earlier algebra related to two-way classification, the interaction effect had I minus 1 into j minus 1 degrees of freedom. So, now if you try to find out the degrees of freedom for the error, that will come out to be by subtraction this I j minus 1 minus all these 3 degrees of freedom, and this will come out to be here 0. So, do not you think that now there is no degrees of freedom for this error? So, how are you going to estimate all those means how are you going to conduct the test of hypothesis? Right. So, now this is a problem, and the problem here is that the two factor interaction effect and the random error components, they are subsumed together and they cannot be separated out. Although we said, because we have one observations in a cell, so we cannot estimate it. So, we are assuming it to be 0, but that is our assumption. Means I would say this is the issue with us, that we are unable to measure the or estimate the interaction effect. But interaction effect is not saying that that I am absent. So, what we had done, we simply merged the interaction effect and random effects together, and because of that there was no estimate of sigma square, because we had only one observation in a cell, and if no interaction exists, then the hypothesis that H naught gamma I j is equal to 0 is accepted, and the model simply becomes here y I j is equal to mu plus alpha I plus beta j plus epsilon I j, and then we can proceed further for testing the hypothesis H naught, say alpha I equal to 0 or H naught beta j equal to 0. And in that case the error will have I minus 1 into j minus 1 degrees of freedom, no problem, right. So, now the question here is that suppose the interaction effect is present in the data, and when you try to test the hypothesis H naught gamma I j is equal to 0, then this hypothesis is rejected. That means there is an interaction. The interaction effect is present in the data. So, now in such a case, if we assume that the structure of the interaction effect is such that it is proportional to the product of individual effects, like as if I say here gamma I j is equal to something like alpha I into beta j, this is how we are going to measure it, and this is proportional to it. So, I can write down here gamma I j is equal to lambda times alpha I into beta j. And then in case if I try to construct a test for h naught lambda is equal to 0, then do not you think that it is going to help us? Means if this test h naught lambda equal to 0 is accepted, that means lambda equal to 0, and then obviously this gamma I j will become simply 0. And if h naught lambda equal to 0 is not accepted, then we have to proceed accordingly. So, if we can develop a test of hypothesis for h naught lambda equal to 0, then such a test will serve as a test for non-additivity, right, and it will help us in knowing the effect of the presence of interaction effect and whether the interaction enters into the model additively or not, right. And now the question is how to obtain such a test. So, such a test is given by Tukey's test, and that is called as Tukey's test for non-additivity, and this test requires 1 degree of freedom, leaving I minus 1 into j minus 1 degrees of freedom for random error. So, now let us try to understand how we can develop this test, and you have to be now very careful about the symbols and notations, and please try to follow what I am trying to say. If you have any confusion, then you try to concentrate once again, and I am sure that you can understand it very easily. So, we now assume that this departure from additivity can be specified by introducing a product term in the model. So, we can write the model here as say mu plus alpha I plus beta j plus lambda times alpha I into beta j, where we have the same setup that I goes from 1 to I and j goes from here 1 to capital J. And now, we are assuming here that the constraints they are satisfied, that is summation over I alpha I is equal to 0 and summation over j beta j is equal to 0. Now, one thing we have to now understand, once you are trying to write down this interaction effect in the framework of lambda times alpha I into beta j, and suppose if lambda is not equal to 0, then there are here two parameters alpha I and beta j. Now, you have to recall the definition of a linear model. We have learned in the theory of linear model and linear statistical inference that a model is said to be linear if it is linear in parameters, right. Sometimes people get confused that it is linearity with respect to the variables. No, the fundamental definition says that a model is said to be linear if it is linear in parameters. And that is why if you try to write down here a model like y equal to beta 0 plus beta 1 x square plus epsilon, this is also treated as a linear model, and whereas if you try to write down the model here as a beta 0 plus beta 1 square x plus epsilon, this is treated as a non-linear model, right. So, this definition should be clear in your mind, and when I am trying to say linear, that means the power of the terms of the parameter should be equal to 1. But now, if you try to see here that in this term here there are two parameters alpha I and beta j. So, the power of the term for these parameters does not remain as 1, and so when lambda is not equal to 0, the model becomes a non-linear model, and once the model becomes non-linear, then the least square theory of linear models is not applicable. Well, the theory which you have developed for the least square estimators which are obtained by applying the principle of least square, that is over a linear model, and that is how you have derived different types of setups under the Gauss-Markov theorem. But in case if the model becomes non-linear, then yeah, least square can be applied, but then we have a different type of theory and we have a non-linear least square estimation, but definitely we are not considering it here. What are we considering here? This is the least square principle over the linear models, and that is why we have applied all sorts of results up to now. Right. So, now we have this trouble. So, but now we have to solve this problem, because by saying that there is a trouble you cannot escape. You have to suggest a solution. So, now let us try to first understand the role of different values in this setup, right. So, now I would request you that for some time you try to just concentrate on this slide and try to see what happens to the mean of all the observations under this type of model, and I am not making here any comment whether my lambda is 0 or not. Right. So, if you try to see here, the arithmetic mean of all the available observation is here y bar double naught, which is here 1 upon capital I into capital J, that is the total number of the observations, into double summation over I goes from 1 to capital I, j goes from 1 to capital J, y I j. Now, what you try to do here? You try to write down y I j in terms of the model. So, this will become here mu plus alpha I plus beta j plus lambda times alpha I beta j plus epsilon I j. Now, what you do? You try to bring this summation inside the brackets. So, now if you try to see what will happen. If you try to see here, this will become here 1 over I j double summation I j times here mu, and it will become here, see here I times j upon I times j into here mu, and this will simply become here mu, and this is here given here, you can see this is here mu. Now, if you try to solve the other part, this will become here 1 over I j summation over I summation over j, say alpha I, and this is equal to, see here j over I j summation over I alpha I. So, this j get cancelled out and this term is written over here. And similarly, if you try to solve the second part, this is 1 over I j double summation I j times here beta j. So, this will become here I upon I j into summation beta j summation over j. So, this I will get cancelled out and you will get here this term. Right. Now, you see the most important part, what is going to happen. When you try to consider now here 1 over I j double summation, say lambda times alpha I beta j summation over I and j. So, this becomes here lambda upon say I into j, and this I can write down here summation alpha I summation over I and summation beta j, where summation is over j. Now, you have assumed this summation alpha I and summation beta j to be here, say here 0. So, this I can write down here, both these terms are 0, and so this entire term becomes here simply here 0. And then after that, yeah, means you are trying to take the average of arithmetic mean of all those epsilon terms, which is coming here as say epsilon bar double naught, no issue. So, now you can see here in this case what is now happening. This alpha I is equal to 0, this summation beta j is equal to 0, and the third term is also becoming here 0. So, now what you have here in your hand is y bar double naught is equal to mu plus epsilon bar double naught, and if you try to take the expectation on both the sides, the expected value of y bar double naught comes out to be mu, and mu hat equal to y bar double naught is an unbiased estimator of mu. So, now in this case you can see here whether you have used lambda equal to 0 or not. This mu is estimable and mu can be unbiasedly estimated by the mean of all the observation. Now, similarly, you try to do the similar exercise with y bar I naught and y bar naught j. So, when I try to consider here y bar I naught, so by definition this is 1 upon j, summation j goes from 1 to capital J y I j, and this is here 1 upon j, and now you try to write down here y I j here as earlier. So, now when you try to take this summation sign inside the bracket, then the first term will remain here as say mu, no problem. The second term will be your here 1 over j summation over j and alpha I. So, this will become here j upon j times here alpha I. So, this becomes here simply alpha I. Now, when this summation sign comes over here on beta j, then this becomes here 1 upon j summation over j beta j, and now you have assumed that summation beta j is equal to 0. So, this term becomes 0, and for the remaining part this becomes here lambda into alpha I 1 upon j into summation over j beta j, which is equal to here 0. So, now this term also become equal to 0, and you have here y bar I naught is equal to mu plus alpha I plus epsilon bar I naught, right. So, if you now try to take the expectation on both the sides, since expected value of epsilon I j is equal to 0. So, expected value of epsilon bar I naught will also be equal to 0, no problem in understanding this thing. So, now I can write down here expected value of y bar I naught is equal to mu plus alpha I. Now, you already have obtained an unbiased estimator of mu. So, you can write down here that alpha I is equal to, see here, expected value of y bar I naught minus mu. So, you can obtain here the alpha I hat by here y bar I naught minus mu hat, and now mu hat you had obtained here as a y bar double naught. So, I can replace here and I can obtain here an estimator of alpha I, which is given here y bar I naught minus y bar double naught. Now, do you recall that what is this estimator? When you conducted the two-way analysis of variance without interaction, then you had obtained the same estimator of alpha I. And in this case also, you have not made any assumption that lambda is equal to 0 or not, but still you are getting here the same estimator of alpha I. Now, you can do the similar exercise with y naught j, and you can obtain here very easily that beta hat j will come out to be here y bar naught j minus mu hat, which is equal to y bar naught j minus y bar double naught. So, now you can see here both the estimators, this alpha I hat and beta j hat, they are coming out to be the same that you had obtained earlier in case of two-way analysis of variance without interaction. But once again I will repeat that it is very important for you to keep in mind that you have obtained the estimators of mu, alpha I and beta j irrespective of lambda is equal to 0 or not, right. We have observed that mu hat, alpha I hat and beta hat j, they remain the unbiased estimator of mu, alpha I and beta j respectively, irrespective of whether lambda equal to 0 or not. And if you try to observe that expected value of y I j minus y bar I naught minus y bar naught j plus y bar double naught is coming out to be lambda times alpha I beta j, right. That has been obtained very easily that you have to write down here this model here y I j is equal to mu plus alpha I beta j plus lambda times alpha I beta j, and then you try to write down here say expected value of here y I j and try to bring this part on the left hand side. So, this I can write down here minus mu hat minus alpha I hat minus beta j hat, and this is equal to here lambda times alpha I beta j. And so, once you try to substitute here the values of mu hat, alpha I hat and beta j, hat j, you can find here that this expression comes out to be like this, that expected value of y I j minus y bar double naught minus y bar I naught minus y bar double naught minus y bar naught j minus y bar double naught. This is coming out to be lambda times alpha I beta j, and you can see here I have tried to express these three terms in the format of an elementary contrast also, right. Now, I come to another aspect. Now, I would simply request you that you simply close the part 1 part. Now, I come to second part of this problem solving approach. Now, I am simply forgetting for a while that whatever we have obtained, and I simply try to obtain the least square estimates of mu, alpha I, beta j and lambda based on the least square theory, that we try to minimize just like means earlier double summation epsilon square I j, and I try to replace this epsilon I j by here y I j minus mu minus alpha I minus beta j minus lambda times alpha I beta j, and let me try to write down this thing here as say S I j. So, I can express this sum of square as here S is equal to double summation S square I j. So, now what I want you to observe here, that try to use the same approach that you had used earlier, that you try to partially differentiate with respect to mu, alpha I, beta j and lambda, and then try to solve those equations and try to see what happens, what is the outcome. So, now that is what I am trying to now do here, that I am simply trying to differentiate capital S with respect to mu, with respect to alpha I, with respect to beta j and with respect to lambda, and I am trying to substitute them equal to 0 to obtain the normal equation, and then I try to solve them. So, when I try to partially differentiate S with respect to mu, then there is no problem, and I am getting here mu hat is equal to y bar double naught. So, there is no problem, means I can estimate here mu without any issue. Now, I try to solve the normal equation for alpha I, that a partial derivative of S with respect to alpha I is equal to 0. This is coming here summation over j 1 plus lambda times beta j into S I j is equal to 0. And similarly, if you try to obtain the normal equation, this partial derivative of S with respect to beta j and put it equal to 0, and try to solve them and try to see whether you can obtain alpha I hat and beta j hat. Once you see that you cannot obtain it here, you will get something, but you will not get a estimator of this alpha I or say beta j, even if you try to use the condition summation alpha I equal to 0 and summation beta j is equal to 0, because this is actually a non-linear model. Right. Now, when you try to consider the normal equation partial derivative of S with respect to lambda is equal to 0, then we have this equation double summation alpha I beta j into S I j is equal to 0. Now, you try to substitute here the value of S I j. So, this is y I j minus mu minus alpha I minus beta j minus lambda times alpha I beta j, and put it equal to 0 like this. So, now if you try to solve this equation and try to use that summation alpha equal to 0, summation beta j is equal to 0, then you can obtain here lambda is equal to like this double summation alpha I beta j y I j divided by summation alpha I square summation beta j square like this, right. And let us try to indicate this value by lambda double tilde. You can see here I have made here lambda and tilde and one more tilde here, and then you have to keep in mind this symbol, that what is this expression. Now, if I ask you, can you obtain here the value of lambda? The answer is no. Why? Because here alpha I and beta j both are unknown to us. So, now one simple solution to solve this problem is that if somehow the values of alpha I and beta j are known to us, then we can solve them. Right. So, now the next question is how to obtain such values and how to obtain finally the value of lambda. Right. So, lambda is that value which is indicated by lambda double tilde, which is the value of lambda which is obtainable only when alpha I and beta j are known to us. Now, the question is, this alpha I and beta j are not known to us, because you cannot estimate them from here. You see, you just cannot estimate it. So, now we have here a solution. We had obtained earlier and we had established actually that either we try to take lambda equal to 0 or not, the estimate of alpha I and beta j can be obtained, right. And the unbiased estimator of alpha I was obtained here as a y bar I naught minus y bar double naught, and an unbiased estimator of beta j was obtained here as a y bar naught j minus y bar double naught. So, now can you substitute these values in this lambda? Because now there is no constraint that these values are going to be dependent on lambda or not. So, we try to do one thing now. You have to be very careful now that how are we trying to solve this problem. We are simply trying to estimate the values of alpha I and beta j externally. What is the meaning of externally? If you try to see, here you started using the principle of least square. Here in this case you have obtained the value of lambda, but that is known to us only when the values of alpha I and beta j are known to us, and since they are unknown to us, so you cannot find here the value of lambda. So, now I am requesting one of my friend, you can say like this, to supply us the value of alpha I and beta j. So, my friend goes to the data values and computes the value of alpha I hat like this and beta j hat like this. And my friend tells me, well, you can use this value in place of alpha I and beta j, because these are the values which are going to be true when your lambda is 0 and when your lambda is not 0. So, now what else do I want? So, I simply try to replace the values of alpha I and beta j in this expression of lambda. So, you can see here I am replacing alpha I and beta j by alpha I hat and beta j hat, and similarly here alpha I is replaced by here alpha I hat. So, we have summation alpha I hat square, and similarly we have here summation beta j hat square, and I try to multiply and divide by here this factor I j in the numerator and denominator. So, I can write down here as a I j here, and I try to club j with summation alpha I square and I with summation beta j square, right. Now, here comes a confusion. The confusion is that if you forget the way you have obtained these values, and if you simply try to look at this structure, this is a function of alpha I hat, beta j hat and y I j. So, it appears that alpha I and beta j hat here, this alpha I hat and beta j here, they are also random, but that's a big question mark. Yes, Yij, this is a random, no issue. But now you have to understand one thing here, that alpha I hat and beta j hat, these are the value here, these two values alpha I hat and beta j hat, they are obtained externally. So, somebody has obtained the values using some data, and you can say in very simple language that these are some numerical values. So, now once you write down here them as numerical values, do you think that they are going to be random? No. But the problem here is that sometimes we get confused when we forget that alpha I hat and beta j hat, they are not the numerical values, but they are some estimators, and that is correct also. Means this confusion is very logical, because this is how the language of statistics has been developed, that whenever we are trying to write down some alpha hat or beta hat, they are statistics and they are the function of random variables. So, they are also random variable, but here in this case we have to be careful that how are we going to use it in this place. Means as such alpha I hat and beta j hat, they are random variable because they are depending on the data, but when I am trying to use them only here, then they are going to be treated in a different way. So, now after this my problem is now here solved, and I have obtained the value of lambda as like this. I simply try to replace here the values of alpha I and beta j here like this, and then here Yij, and whatever are my quantities here in the denominator like this here, they are simply I am indicating them by SA and SB, where SA is the same quantity j times summation over I alpha hat I square, which is equal to here j times summation over I y bar I naught minus y bar double naught whole square, and SB here S is I times summation over j beta hat j square, which is equal to I times summation over j y bar naught j minus y bar double naught whole square. So, now you can see here this value I am going to indicate by lambda hat, which is some known value to us, right. Known value, that means the values of alpha I and beta j are known to us, but you have to keep in mind that this is going to depend on Yij. So, lambda hat is a function of Yij only, right, including your this SA and SB, they are also some known quantities. So, alpha I hat, beta j hat, SA, SB, they all are known to us, right. So, now if I ask you a simple question here, suppose if you have to find out the variance of this lambda hat, then how are you going to find out the variance? Means my answer will be, I simply have to consider Yij as a random variable, and then I have to consider all other terms in this expression as known and constant, right. So, now my next objective is to find out the variance. So, in order to just help you, I will try to go more simply, and first I try to consider here the estimator lambda double tilde, where we had assumed that alpha I and beta j are known to us, so that you can see that how we can obtain the estimator, which is easily understandable. So, this will simply become here the square of this quantity into double summation alpha I square beta j square into variance of Yij, because alpha I and beta j are known to us. So, this variance of Yij is simply here sigma square. So, this term will come out to be here like this, and if you simply try to solve it, this will come out to be sigma square upon summation alpha I square into summation beta j square, right. And all other cross product terms here will become 0, because the observations are independent. So, their covariances are going to be 0 for all I not equal to k. Right. So, now you have obtained the variance of this lambda double tilde. Now, if you want to use the same methodology here again, that you are going to obtain the value of alpha I and beta j using the unbiased estimator externally, and then you are trying to substitute them here, then what will happen? Let us try to see. So, that is only a matter of now symbols and notations for you. So, when alpha I and beta j, they are estimated by alpha I hat and beta j hat, then we try to substitute their values in the variance of a lambda double tilde, and then we actually we are trying to then obtain the variance of lambda hat, because lambda hat has been obtained by substituting the values of alpha and beta by their estimators alpha I hat and beta j hat in the lambda double tilde. So, basically we are now trying to obtain here the variance of lambda hat, which is equal to here sigma square upon summation alpha I hat square into summation beta hat j square, right. And if you try to multiply and divide it by here the term here I j, then you will get here this variance of lambda hat as I j sigma square divided by S A into S p, right. So, but remember you have to that here this alpha I hat and beta j both are known to us. So, you can now have this quantity, right. Now, I try to come back once again and try to compile all the results whatever we have obtained in the earlier steps. So, now I can see here that if I try to find out the expected value of lambda hat. So, now if you try to suppose that if lambda is equal to 0, means I will just give you here a hint why I am trying to do it now. Now, I want to develop a test statistics. So, as soon as I write lambda is equal to 0, that is the statistics under H naught, because you have to remember now you were trying to do or you were trying to develop the statistic for testing the null hypothesis H naught lambda equal to 0. Because what really happens that in this procedure there are several steps, and many times students forget that what they were trying to do actually. So, that is why you have to recall once again. Now, if lambda is equal to 0 and if you try to find out the expected value of lambda hat for a given value of alpha I hat and beta j hat for all I and j, this will simply come out to be here like this expected value of this quantity, right. And now, if you try to simply try to substitute here the value of y I j from the model, means you have to simply write down here mu plus alpha I plus beta j, since lambda is equal to 0 from here. So, you can write down this quantity as 0 plus epsilon I j and divided by the summation alpha I square summation beta j square. Now, you can see here if you try to take this expectation sign inside and using the constraint that summation alpha equal to 0, summation beta j is equal to 0, all these terms they will become simply here 0, and this comes out to be 0. So, that means expected value of lambda hat for given value of alpha I hat and beta j hat, this is 0, right. And you have to now understand that lambda hat is only a function of y I j, and lambda hat has got a mean 0 whether your lambda is equal to 0 or lambda is not equal to 0. That means, either H naught is true or H naught is not true, right. And y I j's are assumed to be normally distributed. So, lambda hat will have a normal distribution with mean 0 and variance I j sigma square divided by S A S B, which is the variance which you have obtained here, right. So, now you have obtained the probability distribution of this lambda hat, but the main part was that okay, how you have obtained it, because there is a small trick here that you are trying to write alpha I hat and beta j hat, which means they are the random variable according to our statistical language, but they are actually here the known values. Now, there is no issue. Now, the story is 100% clear. So, in case if you try to recall the definition of chi-square random variable, and you try to write down here the statistic lambda hat square divided by variance of lambda hat, this comes out to be here like this, means I j double summation alpha I hat beta j hat y I j whole square divided by sigma square S A S B. And if you simply try to substitute here the values of alpha I hat and beta j hat, you get here this expression, right. And then in case if you simply try to write down here the expression and simply try to simplify it here, you get here this quantity like this one, right. And I am simply trying to indicate this quantity here as a Sn upon sigma square. So, this Sn is this term here, from here to here, like this one. This is your here capital Sn. Now, if you try to see what is the probability distribution of this Sn upon sigma square, this is only a sum of squares of a standardized version of normal distributed random variable. So, there is only one random variable. So, this quantity, this statistic lambda hat square divided by variance of lambda hat, this is going to follow a chi-square distribution with 1 degrees of freedom, right. And this quantity here Sn, which is given by this quantity I j double summation y bar I naught minus y bar double naught into y bar naught j minus y bar double naught into y I j minus y bar I naught minus y bar naught j plus y bar double naught whole square divided by S A S B. This is the sum of square due to non-additivity, right. So, now the one question comes here that you have seen earlier, that S A B upon sigma square, which was given by this quantity, follows a chi-square distribution with I minus 1 into j minus 1 degrees of freedom, right. So, now means if you try to see here this Sn upon sigma square minus S A B upon sigma square is non-negative and follows a chi-square distribution with I minus 1 into j minus 1 minus 1 degrees of freedom. But now, how? That is the result which I am telling you, but the question here is how it is happening. So, the reason for this statement is as follows. You had considered the model y I j is equal to mu plus alpha I plus beta j plus non-additivity term plus epsilon I j, and now using the analysis of variance technique, you have considered the total sum of squares and you have partitioned it into, say, sum of square due to A, sum of square due to B and sum of square due to non-additivity, say here Sn plus sum of square due to error. So, now you can see here that SSE comes out to be TSS minus SSA minus SSB, that was your earlier, minus Sn. So, now this Sn is involving only 1 degrees of freedom. So, this TSS minus SSA minus SSB, they have got the degree of freedom I j minus 1, I minus 1 and j minus 1 respectively. So, if you try to compute the corresponding degrees of freedom in this case for this SSE, then this will come out to be simply I minus 1 into j minus 1 minus 1, right. So, now you have obtained the distribution, you have obtained its degrees of freedom, but now there is one problem. The problem here is that when you did the Fisher-Cockram theorem, then Fisher-Cockram theorem was trying to write the statements like this: Q can be partitioned into 3 orthogonal sum of squares, say, or 3 orthogonal component Q1 plus Q2 plus Q3, that means they are additive and their degrees of freedom are going to be additive. But in this case, you are trying to consider the difference. Means you are trying to write down here Q3 is equal to Q minus Q1 minus Q2, and you are trying to employ a result which is similar to Fisher-Cochran theorem. So, I would like to point out here, you are not using here the Fisher-Cochran theorem, but you are using a result which is very similar to the Fisher-Cochran theorem, and that result is like that, which is given here in this slide. So, we assume that SSE is greater than 0. Well, that will happen in this case, but the result is that if Q, Q1 and Q2 are the quadratic form such that Q is equal to Q1 plus Q2, where Q is following a chi-square distribution with A degrees of freedom, Q2 is following a chi-square distribution with B degrees of freedom, and Q2 is non-negative, then Q1 follows a chi-square distribution with A minus B degrees of freedom. And this result actually ensures that Sn upon sigma square minus Sab upon sigma square, which you have considered here, this is non-negative, right. And one can prove that this Sn, which is the sum of a square due to non-additivity and SSE, they are also orthogonal, right. So, now you are done. Now, you have done all the things. So, now you can write down here the statistics for testing the null hypothesis H naught lambda equal to 0 like this. Now, you have got here the quantity Sn upon sigma square, which has got a chi-square distribution with 1 degrees of freedom. So, we try to write down here Sn divided by sigma square divided by 1, that is the numerator of a statistics, and then we try to use here the distribution of sum of a square due to error SSE. So, we try to write down here SSE upon sigma square and divided by the corresponding degrees of freedom I minus 1, j minus 1, minus 1. Now, means one can show that the quantities in the numerator and denominator, that is Sn and SSE, they are independent. They are actually in the form of a quadratic form. Then I can simplify it, and this comes out to be that I minus 1 into j minus 1 minus 1 into Ssn upon SSE. This follows a central F distribution with the degrees of freedom 1 and I minus 1 j minus 1 minus 1 degrees of freedom under H naught, right. So, now the decision rule comes out to be reject H naught whenever F is greater than F with 1 and I minus 1 j minus 1 minus 1 degrees of freedom at alpha level of significance, right. So, now you can just compile all the results whatever you have obtained in the form of the ANOVA table, and the initial ANOVA table, when there was a confusion that the error degrees of freedom were 0, this is now solved. And you can see here that the ANOVA table for testing H naught lambda equal to 0 is like this. The source of variation, as earlier there are factor A, factor B, an error, but now we have added here one more term due to non-additivity, which is here n. And now, the degrees of freedom for the sum of squares due to factor A are I minus 1, for factor B they are j minus 1 as earlier, and now the degrees of freedom of this error and non-additivity, they are divided into two parts, such that due to non-additivity there is 1 degrees of freedom, and the remaining degrees of freedom which are I minus 1 into j minus 1 minus 1, they are now going to error, right. And total degrees of freedom are here as usual as earlier I j minus 1, and the corresponding sum of squares are SA, SB, SN, SSE and TSS. That is the standard thing that you used earlier. Now, based on that you can find out here mean square, MSA, MSB, MSN that you have obtained here as say here SN, because the degree of freedom here is only 1, and then MSE, and then you try to take the ratio of this MSN and MSE, and you can obtain here the F statistics, which can help you in testing the hypothesis H naught lambda is equal to 0, right. Okay, so now we come to an end to this lecture, and you can see here that was pretty interesting lecture in the sense that you have done something very different. Well, that the algebra is extremely simple. The development of the test, it is very simple, very straightforward. There was only one hitch that I have explained you before the beginning of the lecture, that we are going to indicate the estimates of two parameters in our classical language of statistics as say alpha hat and beta hat, which have to be random variable as per the rules of statistics. But in this case, at the place where we are trying to use them, or the way we are trying to use them, we are treating them as some known quantities, although they are based on the data itself, because alpha I and beta j, they are going to be obtained on the basis of given sample of data only. So, that is only here a point where you have to be very careful when you try to understand this development. The implementation of the test, the algebra expression, they are not difficult at all. Right. So, now I will stop in this lecture, and I will also stop in the development of this analysis of variance. We have covered one way, two way, with and without interaction. And I personally believe that if you have understood these three analyses of variance, their steps, their minor details, after this if you have to develop any analysis of variance of any order model, say third order, fourth order, fifth order, you can do it very easily without any problem. And I also have shown you that either you are trying to use the principle of least square or the method of this likelihood ratio test, you are going to get the same outcome. So, now it is up to you that whatever approach you want and whatever approach is applicable in the given situation, you can use it. So, now that time has come where we have to see that where are we going to apply this analysis of variance. In the data has to be compatible so that we can apply these tests. And in the beginning I told you that in this course there are two aspects. One is the analysis of variance and another is the design of experiment. So, now from the next lecture I will try to pick up the design of experiments, and then after that we will burst them together. But in order to understand those design of experiment, it is very important for you that you have revised all this analysis of variance very well, because there I am not going to explain it anymore, but I will simply say use one way, use two way, etc. So, you try to have a quick revision, thorough revision, try to understand it, and I will see you in the next lecture. Till then, goodbye.